Additive manufacturing is one of the most important engineering advancements in recent years. With fused deposition modeling, we can make parts that have complex internal shapes, infills, patterns, and densities. This creates an important question. How can we predict how these printed parts will perform without using expensive trial and error testing? As finite element analysis software improves, we can now model 3D printed parts with much more detail. But a simulation is only valuable if it matches actual experimental outcomes. That is why it is important to understand how accurate these models are and how infill affects the strength and behavior of the printed parts. The final deliverable for our project is a document of recommendations and procedures that explains how to produce, repeat, and verify FDM models in finite element analysis. Our goal is to help future teams create more reliable simulations and reduce the need for unnecessary testing.
Cummins Aerospace has commissioned our design team to provide a system to predict the material properties of 3D printed products. Our project addresses real engineering needs by integrating simulation with additive manufacturing, generate recommendations for optimized strength-to-weight performance. The Hellhound S2 and S3 platforms shown here are Cummins Aerospace's 3D printed, jet-powered unmanned aerial systems. Their lightweight design relies on efficient internal structures to maintain stability and withstand dynamic flight loads. Our strength-to-weight optimization method applies directly to similar components. Even small weight reductions enhance range, loiter time, and payload capacity. By using PETG and FDM printing, we enable cost-effective, material-efficient fabrication for prototype hardware and low-expense UAS components. This approach reduces waste, extends machine life, and supports data-driven design for systems like the Hellhound.
Hello, my name is Jared Land. I am a mechanical engineer, and I am the project lead on Senior Design Team 2507.
My name is Lance Oldham. I'm a mechanical engineer.
Hello, I'm Ali. I'm a material science engineer.
My name is Ryan McCabe, mechanical engineer as well as procurement lead.
I'm Ashton Atakai, and I'm the systems engineer.
Hi, my name is Khalid Al-Kahtani. I am an industrial engineer.
Hi, my name is Kieran, and I'm an industrial engineer.
Our approach combines simulation, prototyping, and experimental testing. We begin by researching different testing variables and decide on focusing how different infill patterns and densities affect part strength. To validate our models, we designed test samples and 3D printed them using FDM printers with a material called PETG. Each sample was printed with a controlled internal structure and consistent process parameters. We are currently performing 5 types of mechanical testing: impact, tensile, shear, permeation, and finally bending. These tests provide a comprehensive understanding of material behavior under different loading conditions and infill percentages.
Tensile properties and young modulus were measured to understand how the material stretches, how stiff it is, and when it starts to fail under pulling force. Shear test. The goal of shear test was measured to see how much sliding force the material can handle before it breaks. For bending test was evaluated to learn how the samples behave under flexing loads and how much they can bend before failure. Water absorption was tested to understand how much moisture the PETG material absorbs over time and how this affects its performance. Impact test. The goal of this test was measured to determine how well the material absorbs sudden shocks or hits and how the infill affect toughness. For our safety, our goals were to reduce risk, ensure proper machine operation, and protect the team. We completed safety training, used protective glasses, and followed machine operation procedure during printing and testing.
Our project design centers around the development of structural analysis methodology. This is an iterative design that integrates digital simulation, design optimization, validation of test parts, and experimental testing to evaluate the performance of 3D printed PETG components. This design is a repeatable analytical process that aerospace engineers can apply to any 3D printed component to optimize for strength-to-weight ratio, reliability, and efficiency. Prioritizing the sponsor needs influence the tests used and variables tested.
After collecting experimental data, the mean variation and confidence intervals were calculated for each test. A two-way ANOVA test was then applied to see if there were any correlation between the experimental factors. For the test that showed a significant enough correlation between the factors, a Tukey multiple comparison test was used to figure out which factors affected the results the most. A regression equation was formulated to characterize the effects of different factors to prioritize them. FEA models were made for each test part and compared to the experimental results to help create optimized strength to weight ratios. Due to modern FEA software progressively becoming more advanced, the need to understand how closely the models match real-world behavior has become increasingly important. The system was designed to use industry standards for testing, software, and simulation so it can be utilized with ease by Cummins Aerospace. The ability to verify the FEA models with experimental results allows for the user to attain material property standards and verify structurally weak points to optimize reinforced areas for increased strength to weight ratios. The performance of our design was guided by the system requirements that were formulated from the needs of our sponsor and overall goal for the project. Several key requirements included that the process must be repeatable and efficient for engineers to follow so it can easily be integratable into Cummins Aerospace. The system must also use CAD software like SolidWorks for modeling and then FEA software like ANSYS and NTOP for structural analysis. A strength to weight recommendation is also set to be put forth, outlined by the experimentation and modeling. As a team, all of these goals were accomplished with all requirements tracked and verified with a system verification matrix. Our sponsor wanted results with a 90% confidence interval and a 10% margin of error.
How good are results? Our sponsor wanted results with a 90% confident interval and a 10% margin of error. We were able to exceed these exceptions with a 95% confident interval and 8% margin of error. By doing multiple rounds of testing, sample sizes could be chosen that satisfy our accuracy requirement. For this project, all of the quantitative data was collected with an 8% margin of error.
Our first test result shows that simulation matches the real world tests. During testing, we noticed that for all samples and all conditions, the infill percentage has an opposite the relationship with the Young modulus. This means when you increase the infill and make the part more solid, the material became less elastic and more stiff. This helped designers choose what matters more for their part, flexibility or more stiff, making the material useful for many different applications.
We'd like to extend our sincere thanks to our mentor Steve Larimore and our sponsor Cummins Aerospace for their continuous support, expertise, and guidance throughout this project. Their involvement was essential to our progress and success. We also want to thank all the team members of the University of Arizona Engineering Department who helped facilitate and support this work. Thank you for watching our presentation. We hope our work helps advance the accuracy and efficiency of structural analysis for 3D printed components and contributes to future developments in this field.